Everybody, welcome to Code Workshop. Today we're going to build a tutorial that will give us an intuition for the Vector3 data type in Three.JS. And we're going to use Vec3s to simulate some semi-realistic motion using forces and velocity and all kinds of cool stuff. So here's what we're going to build. It's pretty simple. This cone will follow the sphere around the scene, but the cool thing about it is it sort of has an orbiting behavior where it turns slowly, and it also points in the direction of motion. So using some pretty simple primitives, we can accomplish all of this. And then at the end, I'll show you how to tweak some of the parameters of the simulation so that you can get whatever type of movement you need for your particular use cases. So with that said, let's dive right into building this project. Since we just want to focus on Vector3s in this tutorial, we're going to start out with some boilerplate to set up our scene and provide some debugging tools that will let us understand what's going on with the vectors a little bit more clearly. Before we actually start coding, let's go over what's already in there just so you don't have to worry about it anymore. This is our scene. The function that we're going to be implementing, this mover component, is where we're going to put all of the code that powers the movement of the cone. We already have this component called the attractor. The attractor is just this teal sphere here, which represents the direction that our cone is going to move towards. That's why it's called the attractor. We're going to set it up in a way where the cone is attracted to this position. One kind of interesting thing about the way this works is it uses this raycaster object, which is part of Three.JS. And a raycaster is a way of taking a two-dimensional position in the scene. In our case, it's the mouse position, and projecting out into the 3D space. And so that's what we're doing here on line 17. The raycaster is casting a ray at 5. And 5 in this case is the distance out into 3D space that we're casting. So if I change this to, say, 10, you'll notice that the sphere gets a lot smaller. It's actually farther back in the scene. If I move it to 1, it's much bigger and closer. So we'll leave that at 5. And then this second parameter is actually where you want to, well, what it is it's a Vector3 that we want to update with the results of casting that ray. So this is a ref that is attached to our actual sphere geometry. So that's why the sphere is being updated. This line here is casting a ray and then setting the current position of the sphere to be that ray. Okay, and then we also have a background component. The background component is this grid, and that's just there to make it a little more obvious how the cone and the sphere are moving around 3D space. Without anything there, it's just kind of hard to tell where everything is moving. And then finally we have our scene, which just composes all of these other elements together and adds a few lights and also adds some orbit controls, which is why we can click and drag around and have everything rotate. If you were to comment that out, you would just not be able to rotate the scene anymore. Okay, so this is our starting point. We're just gonna start with this and get to building our moving cone. So the first thing we want to do to implement our mover component is to return some geometry. So let's add our cone to this component. So we're going to return something, and that thing is going to be a cone from dry. So we can add that to the imports from dry here, and then we'll have access to a cone. So I'll add a component there called cone. And then whenever we add a component, we want to add a child component for the texture. So just like in the attractor, we'll use the mesh Lambert material, and we'll make that color hot pink. Okay, let's save that. Nothing's updated yet because we're not using the mover component. So let's go down to our scene, and within the scene, we'll add our mover. Oops. Type that right, and there we go. There's our hot pink cone just sitting right in the middle, kind of a weird size. So going back up to our cone geometry on line 11, we can add in some arguments to the cone. So a lot of the geometry in React 3 Fiber has this args prop, and the reason it has an args prop is because in Three.JS, which React 3 Fiber is built on, when you instantiate a geometry object from a geometry class, you call the constructor with some args, and that's what those args relate to in the props. So for cone geometry, the args are the radius, which is a float or a number, height, also a float, and radial segment is an integer. And for pretty much all of the geometry types in Three.JS, in the docs, they have a really handy little demo where you can adjust some of those args. So if you want to understand better what they do, I always recommend just searching for whatever type of geometry you have in Three.JS and then coming in here, and you can mess around with the values a little bit. So we kind of see what radius does. It closes up the radius of the bottom of the cone. The height, I think, is pretty obvious what it's going to do. It's going to lengthen out the cone. And then radial segments is how granular the actual cone shape is. So you might be thinking, if you drag this all the way down to 3, you can maybe have a pyramid, and that's true, you can. Or a good looking pyramid. But we're just going to make a cone. So going back to our args here, I am going to try something pretty small just because I have a decent idea of like the scale of the scene. We're going to do 0.1 for the radius. You see it update immediately. And so we'll make it a bit shorter, 0.4. I think the segments actually look fine, but we can add a value there just to have a placeholder. Okay. So there's our cone. We can see its default position is right in the center of the scene. That position is actually 0, 0, 0. And you see the orientation of the cone is pointing straight upwards. That is actually going to come into play later when we add the ability for the cone to sort of point in the direction of motion. We're going to learn how to rotate it properly, like using the velocity, which is also the direction. And we're going to convert that into a rotation. So just remember later that the default rotation is just pointing straight up. And there we go. So now that we have our geometry, let's start working on the animation. All right, so the first step in animating pretty much anything in React 3 Fiber is to add a useFrameHook. to the component you want to animate. So the useFrameHook allows us to register some function to call on every animation frame, and that's all sort of handled under the scenes for you. But this is our starting place. So we call useFrame with a function, and so this is the function that will get run on each frame. All right, so you'll probably get an error message when you first type that in. That's just because when you update hooks, React is kind of weird sometimes. So we refresh, everything should be as it was. We're basically just saying every frame do nothing, which is what is happening. So now that we have it doing nothing, let's make it do something. And the thing that we want to do is, first, let's just update the position of the cone manually in some really simple way, just to sort of get some idea of how useFrame works. So in order to update the position, we're going to need a ref to the geometry in React. And that's so that inside of the hook, we can update some of the attributes of the geometry. And so to add a ref in React, it's pretty easy. You just define that ref somewhere in the component. So we're going to call our ref mover ref. And then you use the useRefHook. And in TypeScript, we can give that a type. So we're actually going to make our type, I think we're going to use a group. So I want to do a group, we'll just use this type, 3 group, and then we will just set the default of this to null. Oh, this is capitalized, yeah. Okay, so now we have this ref, we need somewhere to attach it. So we're going to wrap our cone in a group element, and this is just kind of convenient to do so that if later we want to add some more geometry to the thing we're animating, it's easy, we just put it inside the group. It's just convenient to have sort of a local space wrapping all of our geometry for doing transformations. So we will create this group and then add a ref prop to it, which gets past our mover ref. Okay, so now that we have a mover ref, this is going to be defined here. So now we can access that ref inside the useFrameHook. And just to save ourselves some time typing, I'm also going to define a constant called position. And that position is going to be mover ref current is the current value of the ref. So we need that. And it's possible for that to not be defined. So I'm going to put a question mark there. And then want the position. Okay. So now we are assigning the position, and we can do something with that. So first off, let's just try making the X value of the position slightly higher on every frame. So to do that, we can assign to position.x. And if you're paying attention, you're going to start seeing that this vector3 comes up. That is a hint that we're working with a vector3 class object right now, and that is the position. If you hover over that, you'll actually see that with the TypeScript hints. So we're just starting to get into vector3s. So if we assign this to plus equals 0.001, so it's saying that position can possibly be undefined. So let's actually fix that by making this be a new vector3 if it doesn't exist. It's pretty much always going to exist, but just in React, when you use a ref, it may not be mounted right away. So we need to just have a fallback in case it doesn't exist. All right, so we are animating the X position, and it has been happening for a while. So our cone is slowly drifting off to the edge here. If I were to change this to a negative, I can start to bring it back over. Could make it go faster by changing the value that we're adding here. We can also do a Y value, Z value. And that's the basics of animation. We just need to be able to control what we're adding and subtracting from the position on every frame. Now, it's one thing to just do this linearly, where every frame you add or subtract the same amount, but in the real world, animation and motion doesn't really work that way. I mean, not usually anyways. Most of the time, an object has some forces that are being applied to it, like, I don't know, gravity is one obvious one. Also, maybe there's a wind and the wind is pushing the object around, or maybe there's a rocket attached to the object pushing it. There's usually multiple forces at any given moment that are being applied to an object. And then even then, the forces don't just like immediately change the motion of the object. There's inertia and there's friction, and there's just all kinds of things going on. And so we really want to try to model the real world by including some of that in our simple simulation. And this isn't going to be like a fully realistic physics simulation, but it is a good way to do animation that's going to feel natural, even if it's not realistic, even if maybe you just want to have like 100 objects rotating around something that kind of look like balls of energy, or just some kind of a magical effect that you want to create. This is a way to sort of build up that animation and get it to look exactly the way you want it to look through small tweaks of some of the parameters that we're going to add over time. All right. So that said, one of the things that I think is going to help us a lot is if we can follow the numerical updates that are happening as the scene runs. And you'll notice that here in the top left corner, we're showing the position, direction, velocity, acceleration, and force of the mover, where force is force being applied to the mover. But they don't show anything yet. Well, we are going to add that right now for the position. So the position is being updated, but we're not seeing an update here. So in order to make that work, we're going to add some instrumentation, most of which has already been built out in the project. So the only thing that we need to do is add another hook to the top of our mover that we're going to call report position. And then the hook we're going to use is called useInstrumentation. And that we're going to pass in a function called setPosition. All right. And so now that we have this report position variable, we will be able to call that with the position. And there we go. So now it's updating. And since we are adding 0.01 to the Z value of position on every single frame, Z is just constantly getting higher and higher and higher. Let's just kind of prove that that works with all of the values. So now we're seeing all three of them update. Okay, cool. So this is just going to help us sort of reason about how the changes we're about to make to add a velocity and acceleration and everything, just kind of see how they all work together a little bit better. And over time, we'll add some more instrumentation as we go. Okay, so that's the position. We're able to control that now. Let's move on to working on controlling velocity. Okay, so instead of just manually updating these X, Y, and Z values on the position, we want to update the position based on whatever the current velocity of the mover is at any given moment. So the first thing that we need to do is actually have some sort of way of storing what the current velocity is. So let's define actually, let's call this we're going to do let velocity ref equals useRef. And this is going to be our first vector3 that we're going to create manually. And we're going to initialize this as 0, 0, 0. All right. So now we have this velocity ref, which is a new vector3 with the value 0, 0, 0. All right. So what can we do with that? Well, we can use our first vector3 method, and we've secretly been using some of the attributes of the vector3 data type. These z, x, and y values are attributes on the vector3. Going back into our Three.JS docs, we can look up vector3, and it's actually going to tell us that right at the top here. The x, y, and z values are all available to us as properties on the vector3. But we're going to start using some of the methods on this data type as well. And in fact, the first one we want is right here, this add method. So what does the add method do? The add method lets us add another vec3 to an existing vec3. And that's exactly what we want. So we want to update the position with the value of velocity on every frame, because velocity is describing how the object is currently moving. So to do that, we're going to want to add the velocity. So the first thing we want to do is just get a variable here called velocity. And similar to what we did with the position, we'll just kind of like extract that out of the ref. So velocity ref.current. All right. And if you're curious why we're using a ref to store the velocity instead of like state or something, the reason for that is because updating state in a useFrameHook is not a good idea. It's very, it can cause a lot of issues because it's going to make the React component re-render on every single frame, which is, could be 90 frames per second. And so we really want to store any kind of state that we're using in our simulation outside of the React lifecycle and outside of state. So the quickest and simplest way to do that is just to use a ref. There's plenty of other ways we could do that. We could even put that in our store that we have here, but this is just easier to do for this particular demo. All right, so we have our velocity. Now let's try to use it. So instead of adding some value to the x, the y, and the z positions separately, now we could just do position add velocity. Save that. Let's reset this so that we get our cone back in the center. And there's our cone. It's not moving, but we also don't have any errors. So let's try adjusting the default value of this velocity. Maybe we'll do both the x and the y, just to prove we can do more than one at once now. And then refresh again. There we go. So now our cone is moving based on whatever this velocity vector's value is. So nice. All right. So that's interesting and all, but it doesn't really get us where we want to be, where we can have the cone follow the sphere around. And to do that, we're going to need our velocity to update as well. We're going to need the velocity to change depending on where the cone is relative to the sphere, because we always want the velocity to be sort of heading towards the sphere, at least eventually. So next, let's work on that. Let's add some acceleration to control the value of velocity, and we'll also add the force value to control the current value of acceleration. So let's add the acceleration. The acceleration is the rate of change of velocity, and we're going to start by just adding another ref called acceleration ref. We can copy and paste code from velocity ref. And then just like we added velocity to position, we can add acceleration to velocity. So down here, we're going to get another reference to acceleration just to save us from typing everything. Okay, and do velocity add save that. Obviously still nothing happening because everything is zeros. But now, instead of like initializing velocity with some value to see it move, we could try to just change the acceleration. So if we do some values for acceleration here, that, oh, it's really flying out there, and much faster than before too. And the reason for that is that now velocity every single frame is getting 0.01 higher, so it's actually probably ending up pretty high. And luckily, we know we have a way to track exactly how fast that's changing because we can report the velocity now too. So we'll copy this report position line, call that report velocity. Set the velocity. And right underneath where we are updating the velocity, see those numbers roll. So since this is changing so quickly, let's slow it down a little. You can see as this goes up, position changes faster and faster, which is exactly what we want. We want position to change by the value of velocity and velocity to change by the value of acceleration. Now, the acceleration, we need it to also change depending on where the attractor is. So let's work on that next. So now we need to update the value of the acceleration so that it is constantly being adjusted to move us towards the attractor. And the way we're going to think of that is we're going to think of the attractor exerting a force on the acceleration. Now, that's not completely necessary when we only have one force. We could just update the acceleration directly, but you may want to have some turbulence in the motion or have some pressure resisting against the acceleration towards the attractor, or all kinds of interesting things. So thinking of it as a force is probably a good thing to start doing now. And we will go in that direction by creating a value called force that we'll use to update the acceleration. And we can do that here in our useFrameHook. So I think right underneath where we have initialized our position, velocity, and acceleration values, we'll start by actually what we'll need first is to grab the value for the location of the attractor. So let's create a variable called const pointer called position. Make that a new vector3. And this is just going to be a place to hold the current mouse or the attractor position. We could have called this attractor position too. And we'll actually just do the same thing we did in the attractor component and just grab that from a raycaster. So we'll add the raycaster in to the useFrameHook arguments, and that will make it available to us. So we can call raycaster ray at, use the same value that we used. And then we'll pass in this pointer world position vector. And if you remember from earlier, we said that this second argument is where we're going to store the resulting vector3 from casting this ray. So what we end up with is the position of the attractor stored in there. Okay, and so let's actually use that to create our force now. So we'll define a variable called force, and we'll actually start by getting the position of our attractor, and then using another vector3 method called sub, which just stands for subtract. We're going to subtract the current position of the cone. And all this is doing is giving us essentially the difference between the two positions. So the farther apart they are, the bigger this force is, and the closer they are, the smaller it is. That's not how gravity works. So this isn't really a simulation of gravity. It's just a different simulation. You can use any rules you want. So in this case, what we're saying is, like, as the cone gets farther and farther away, apply more and more force, pulling the cone back. And we'll also report the value of this force just so we know what it is. So let's take report velocity, and we'll actually do two more. We'll do report acceleration and report force, set acceleration, set force. Call those two functions where we want to report those things. So I guess right after setting the force, we will report it. So use that force now to update the acceleration. So we'll actually just go acceleration, add force, report acceleration. Now if we refresh the screen, we're going to see all of our numbers pretty much going crazy. And in a minute, we'll learn how to fix that issue. We need to be able to constrain the values of our force, acceleration, velocity, position, etc., to make our simulation behave the way we want it to. If you just sort of randomly add things together, you end up with things kind of being completely out of scale, where we're subtracting kind of a large number that is bigger than our whole scene on every single frame. And so things just grow or shrink completely out of control. And to do that, we're going to create a few constants that we can use as knobs to make adjustments in our simulation. So way up at the top of our file, we're just going to define a couple of things. We're going to define something called force dampening. We'll start that out at 0.01. We'll define an acceleration, dampening, 0.01, and a velocity dampening. Just make them all 0.01 for now, because we don't actually know what we want them to be yet. That just depends on how we want the simulation to behave. And then we're also going to define a couple min and max values for the acceleration and the speed. So we'll do constant max acceleration 1, we have min speed 1, and a max speed 1. Okay. And then we're going to do one more thing. We're going to create some values to use for boundaries so that our cone never leaves the area that we can see, basically, so we can keep it from sort of flying way off in the distance and getting lost. So we'll actually define another called min. This is going to be a vector3 that will set to 4, 2, and 2, which is basically just some point up here in the corner. Another value called max is also a vector3, -4, -2, -2. And you're probably asking yourself, why is the min positive and the max negative? It's just because of the way we're going to use the min and max functions in vector3, and you'll see later why, but try not to think too hard about it for now. Okay. So now that we have all of these variables defined, let's figure out how we can use them to add some guardrails to our simulation so that we can control the way it behaves. First thing we should do is add the guardrails to the position. So that's going to involve setting a minimum and a maximum on where the position of the cone can be. And that way, no matter how crazy everything else gets, the cone just sort of stays visible to us. So let's start with that. Down here, where we have the position, and we're adding the velocity, we can call some new methods that live on the vector3 object. And going back to our docs here, we can look them up. So there's a min and a max. And we can take these and use them to constrain the maximum and minimum possible values of position. So we'll start by doing the min. So if we add .min, min, and then we can call .max, max. That's going to attach our minimum and our maximum to this original position vector. And the reason for that is that the vector3 type has chaining. So whenever you call a method on a vector3, it returns itself so that you can call another method immediately. So we're calling add on the same vector3 that we're then calling min on, that we're then calling max on. And you can add as many of these as you want to. Right. So if we go back and refresh, now we'll see that the cone is jumping around all over the place, but it's never going beyond a certain cube in the scene. And it's actually kind of insane how it jumps around. Even this is kind of an interesting effect by itself, but that's really just because our acceleration and velocity are still going crazy here. So the next thing that I think we should do is add our dampening to the velocity. And dampening is just a way to sort of control the scale of a value. So let's say velocity goes up to 2. Maybe we want it to be 10 times weaker or 10 times stronger. And so dampening is something we want to multiply against velocity. And we will do that here, actually, where we add the velocity to the position. And the reason we're going to do it here where we are adding it is so that we can store the value of velocity undampened in its sort of original state, just in case we want to make future calculations with it. But when we're actually adjusting the position, we will add the dampened value. So to do that, we're going to first clone the velocity. And what that does, it makes a copy of the vector3 so that we're not modifying the original velocity. And then we're going to use another method called multiplyScalar. MultiplyScalar multiplies a vector by a single number, and it applies that multiplication to every element in the vector. So if you were to multiply 1, 1, 1 by 3 with multiplyScalar, you would end up with 3, 3, 3. And the value that we want to multiply the velocity by here is the value of velocity dampening. So we save that, and we fix our typo. Scalar is spelled 2 A's. And you'll notice that things have kind of changed. You can actually sort of see the cone zip around now. It's still jumping around, but it's a lot slower than it was before. In fact, it's exactly the value of velocity dampening slower, so 1%. All right, so we're getting somewhere, sort of. The next thing that we need to do is actually control the speed at which velocity can change. And also we have some max speed and min speed here. And we can use those to set some constraints around the minimum and maximum values for the velocity. All right, so very similar to what we did on position. We're going to a dampening first for the acceleration. So here where we add acceleration, let's repeat what we did a minute ago and clone that. And then multiplyScalar, acceleration dampening. Go back and see what happened. Oh, things are starting to change now. So still getting some pretty weird behaviors, but there's sort of a delay before the acceleration kicks in. Interesting. So now let's add these min and max speed values, but unlike with position where we set a min and a max, we actually want to do this a bit differently because what we're talking about with speed is actually sort of the length of the velocity vector. So the min and max methods that we used on the position are element-wise min and max, where you give the function another vector3, and it's really saying like the x value of the position can't exceed the x value of the max, or can't be less than the x value of the min. And the y value, same thing, z value, same thing. And that's perfect for controlling a position so that it never gets out of a certain bounding box. But for the velocity, what we really care about isn't so much the individual x, y, and z components. It's really the entire length of the vector that we want to control, because the length of the vector is the speed. And that's why we call it min speed and max speed and not min velocity or max velocity, because velocity includes the direction of travel. The speed, we just really care about how fast it's going in that direction. And luckily we have another way to control the length of the vector, and that is with clampLength. ClampLength is another method on the vector3 type that will prevent a vector from ever exceeding a certain length. You can also set a min here. So we'll actually be able to say the speed of the mover should never be below a certain value as well. And let's go ahead and add that in now. If we go back to line 44, where we just applied our acceleration dampening, next we will call clampLength on that same value, and we will pass in min speed and max speed. Save that. Go back and refresh. And now we have a whole different behavior. Now things are not quite so crazy. A little slow and boring. I don't know what you might use this for, but it could be what you want depending on the effect you're trying to create. So this is a good step. Let's go ahead and do the same thing with the acceleration that we just did for velocity, because we have also a min and max acceleration. We also have force dampening that we can apply. So back to acceleration where we're adding the force. Let's go in there. Same thing. Let's clone that. Let's make a copy of it. MultiplyScalar. And use our force dampening value. Okay. And then here, let's clampLength again. And this time we'll use our minimum acceleration, our maximum acceleration. Give that a save. Refresh again. Very slow acceleration here. We'll be able to tweak this later. But before we get to that, let's wrap up one final thing, which is kind of annoying, and that's that the arrow still just points straight up. Let's work on changing that and getting the rotation to update along with the velocity. All right. So to add in the direction, go all the way to the bottom under where we set the position and define a new variable called direction. And we'll just make that a new vector3. And we'll just be using that to sort of hold our work as we kind of build up this direction. So the first thing that we need to do is copy the velocity into this direction object, but without any scale. And what I mean by that is, remember we said the velocity has a length, which is essentially its speed. We need to sort of remove the speed part of the vector and be left with just the direction. And luckily there's a way to do that built into vector3s called normalize. So the first thing we're going to do is use a method on the vector3 called copy, which will take another vector3 and copy its values into itself. So by calling copy on velocity, we end up with those same values inside of the direction. And then you can call normalize, which will strip out the scale of the vector. And to sort of get a look at that in action, we can also report the direction. So report direction, and then back at the top, we need to create a hook for that again. So we add some more instrumentation, and then there we go. And so if you were to actually take these numbers and figure out the length, what you would find is that the length is always 1. It's just exactly 1. And because of the way we have velocity clamped right now, I think we actually have the speed so that it can only be 1. These are the same, but I think if, let's say we change this, let's make it 0.2, 0.2, or those are the wrong things. We'll make the min speed 0.2 and the max speed 0.2. They're actually different now. So the velocity is smaller than the direction because we're normalizing velocity so that the length is always 1, but we've made it so the velocity is always 0.2. So this is bigger. If we made it faster, this direction is actually going to be smaller, and that's just because of the normalize function. All right. Okay, so we'll stop messing with our parameters for now because we're going to leave that to the end after we have the rotation working. So going back down to the rotation, we're currently in a place where we have this direction vector, but we need to actually apply it to the geometry so that we can see our rotation. And the best way to do that is actually with something called a Quaternion. Now, this is kind of a more advanced concept. We don't need to learn exactly how they work, but it's a way of representing a rotation, and it's going to allow us to rotate our cone, which is pointing straight up, so that it's pointing in the direction of travel in a pretty easy way. So let's learn how to do that. Now, the Quaternion is useful, but even more useful is the fact that every piece of geometry in Three.JS has this Quaternion method, which lets us set the rotation using a Quaternion, and that's what we're going to do. So going back here to where we have created our direction, we're going to use our mover ref again. So let's get a reference to that, and then call the Quaternion method, which we just looked at. And we are going to take that Quaternion, which is actually what the current rotation is, and we're going to set it from unit vectors. So that's another method here. And so if we were to go look at that Quaternion type, you would see that Quaternions have a set from unit vector. And the reason that we're going to use that is because it's going to let us use our direction as is to change the rotation. All right. So to use set unit vectors, first we need to pass in what the current rotation is as a vector. So we can actually just use the default rotation here, which is 0, 1, 0, and then take our direction, save that. Remember, direction is just copy of velocity normalized. Let's see what it's complaining about here. To be set from unit vectors. So now we can refresh and see our cone pointing in the right direction. The movement is still really weird. It takes a really long time to get it turned around when we move the mouse. It doesn't feel very responsive. And so that's going to be our final task, is to sort of tweak these various dampening and mins and maxes so that we get something that looks fairly nice. Okay, so let's start our tweaks by making our mins and maxes something a little bit more reasonable. Like, for example, min and max speed means that our speed can never change, so we obviously don't want that. Let's actually make our min speed 0 so that it could stop if it wanted to. And let's make our max speed a little bit slower. So it's very slow and it's not doing a whole lot, but it does at least kind of have a nice responsiveness to the mouse, though. That could be exactly what you want, depending on what you're doing. Like maybe you, instead of a cone, you had a cool fish or something. You make a fish tank where all the fish follow the mouse. You could maybe want it something like this. But let's just keep playing around with the numbers. So maybe you want the velocity dampening to be a little bigger so that the velocity is faster. And remember, velocity is just how fast the speed can change. And so that just gives it a lot more responsiveness in the turning. But the force is still pretty weak. So like it flies past a point pretty far. So let's say maybe we want the acceleration to be stronger so that, let's just say, so that we can get it to kind of track the mouse a little more closely. So we can pull that way up all the way to 1. So now when we move the mouse, things kind of happen pretty quickly. And this is actually pretty nice. I mean, we still get a nice bit of overshot that turns it around after a while. So that's cool. This is probably what I would leave it with, but just to finish up this video, let's try some more interesting, crazy numbers and just be like, what if we don't have any force dampening? What happens then? Well, then you get like almost a perfect tracking because the force is so quickly applied that it just follows like dead on. And as soon as it passes, it's able to adjust the force really quickly. Change the velocity dampening. Now you get very slow motion, but it still changes. It seems like the force is what really dictates like the speed of change. So if we make that really slow, you'll notice that like the position of the mouse almost doesn't matter anymore. And that's the gist of it. I mean, there's no one right way to configure these values. I mean, min speed, it really can't be less than 0 because this is the length of the vector. So the vector length is always positive. Same thing with min and max acceleration. So it's almost redundant to have mins here, except that maybe you want to force it to be higher all the time, which you can do. Get some real wacky stuff going on here. And yeah, you could add more movers to the scene so that you have multiple objects following the mouse. There's a whole lot of things that you could build off of this simple base, and that's why I wanted to do this tutorial, just to kind of like break down motion to like the simplest possible project. And I hope that it is helpful. Feel free to leave any questions or comments in the comment section, and I'll take a look and try to help out if there's anything I can do. All right, thanks y'all. Bye.